we're going to have 5 very interesting papers covering using ML, AI for prefetching and leveraging some of the structure in the front end for efficient instruction delivery, like micro-op cache. So we're going to start the first talk with a new formulation of neural data prefetching. The author, Duong, is a 4th-year PhD student at UT Austin. He's applying machine learning to microarchitectural prediction problems, such as prefetching, cache replacement, and branch prediction. Duong, the floor is yours.
So temporal prefetching is this really powerful idea that involves correlating addresses to other addresses, and it does so by mapping a trigger address A to its successor. So its strength lies in its simple formulation, and this makes it so that it's capable of prefetching any repeated access patterns. And much of the work in temporal prefetching, since it was first introduced in 1997, has focused primarily on reducing the cost of the metadata storage and on reducing the amount of metadata traffic, rather than improving the prediction mechanism itself, which from the beginning was already fairly accurate. That is until 2021, where we see Voyager, the first neural temporal prefetcher. So what Voyager does is it replaces these traditionally used table-based predictors with a specially designed neural network to actually very much eclipse the prefetching accuracy of prior state-of-the-art. And basically, Voyager is significantly moving the needle in temporal prefetching by showing what portion of the prefetching opportunity is achievable if you have a very strong predictor. And it does so by showing that it outperforms idealized temporal prefetchers by a large margin. And these idealized temporal prefetchers are being modeled with no cost whatsoever, so they have unlimited metadata storage, instant metadata access, and no metadata traffic. However, despite these large and immense results, since Voyager was designed as a limit study to study what we can do with temporal prefetching, it's completely impractical across multiple dimensions, and there's not really a clear path to practicality. To just visualize how impractical Voyager is, let this yellow square that you're seeing here represent a 2 megabyte LLC. And you'll see that Voyager requires, in terms of storage, roughly 57 such LLCs. Likewise, let this even smaller yellow square represent the latency between 2 LLC accesses. And Voyager's prediction latency is so slow that it can only issue 1 prefetch every 200 accesses. Overall, Voyager's costs are way too high to scale as it is. So of course, there are a lot of standard machine learning techniques out there that you can use to reduce costs, improve model efficiency, and I've included a short list here. However, the fact of the matter is that these standard machine learning techniques are simply not enough because the storage and latency for Voyager grows with the memory footprint. We can see with these 2 graphs here that even just in a short span of 400 million instructions, a fraction of a second, that Voyager has already increased by 100 megabytes, or 50 LLCs, and 25 million flops, or roughly 60 LLC accesses. To take it to an extreme, if Voyager were to accommodate the entire address space, it would require roughly 6 orders of magnitude more storage than the largest LLMs that we have out here today. The root cause of the matter is that the formulation itself for temporal prefetching is the problem, namely that addresses are simply not suitable as neural inputs or outputs to these neural prefetchers. And the issue, as we've seen so far, is that using addresses forces the neural network to grow with the memory footprint. And furthermore, the correlations learned by these neural prefetchers will be useless across runs because the neural temporal prefetcher will be learning exact address-to-address mappings, which are only applicable to the original run from which it was trained and not subsequent runs. The way we tackle this is that we create a new formulation for temporal prefetching, which is much more amenable to neural data prefetchers. And we do so by inserting 2 layers of abstraction between the neural prefetcher and the address space, and we fully insulate it from directly interacting with the address space entirely. So to show how this works, how well this works in practice, relative to Voyager's 57 LOC size, our neural prefetcher requires 4/10 of a single LLC in terms of storage, and relative to Voyager's 1 in 200 accesses of prefetching, our neural temporal prefetcher can issue up to 7 accesses between 2 consecutive LLC accesses, issue up to 7 prefetchers between 2 consecutive LLC accesses. So the rest of this talk will be organized based on our 2 neural temporal prefetchers. The first of which is unconstrained Twilight, which only partially abstracts addresses away, and this significantly reduces costs. However, as it's still impractical, we're comparing against Voyager here, the current state of the art, in an unconstrained manner, just to compare the difference in power between their respective formulations of temporal prefetching. Next, we have a efficiency-minded version of Twilight, Twilight Lite, or T-Lite for short, which is very close and near practical in terms of hardware costs. And as a result, we compared against Triage, a practical on-chip temporal prefetcher that, while faithfully modeling the metadata storage costs and the prediction latency for the models. So getting into Twilight, the key insight behind Twilight is that temporal streams often have this thing of sparse connectivity. So sparse connectivity is where, given an address, there's often only ever a handful of other addresses that will follow it in any temporal stream. For this example here, this address A is only ever followed by B, C, and D, and nothing else throughout the duration of the program. To show this a little bit more empirically, let's let this rectangle represent all of the opportunity presented by temporal prefetching. If you were to limit a temporal prefetcher to prefetching just the most frequent succeeding address for each trigger, you already cover 68% of this opportunity. If you relax this constraint to only allowing the top 4 most frequent successors, you're increasing to 85% coverage. Relaxing the top 20, you get 94% of the coverage. So really the upshot of this is that all of the many quadrillion other addresses that we're not considering for each of these prefetch decisions only cover a measly 66% of the opportunity, which enables us to make this fantastic trade-off between coverage and neural prefetcher cost. So this gets into our first half of our reformulation, candidate selection. So candidate selection is our abstraction layer for the output of the neural network. And basically, it reformulates the prediction problem from predicting one address from any address in the entire address space to predicting one address out of this list of top n most frequent successors, or alternatively not to prefetch. Under this formulation, our Twilight neural prefetcher only has 21 outputs now rather than having like 2 to the 52. Corresponding to the top 20 and the option not to prefetch. Moving on to describing the ideas that underlie T-Lite. So we just saw that candidate selection resolved the issue with neural outputs. Now we're going to see how to resolve the issue with neural inputs. So Voyager has a neural encoding for every single unique address in the memory footprint, and this incurs an incredibly high storage cost. So the intuition behind our idea is that data of a given type tends to have similar access patterns to other data with the same type when met with a similar context. So using this, we can come to the conclusion that having neural encoding for every single address is redundant and wasteful, and that really puts together our next, the the second half of our reformulation of temporal prefetching, behavioral clustering. So behavioral clustering is exactly what it sounds like, in that you are grouping addresses together based on their prefetching behavior. And from these groups, you only need to assign one neural encoding for each cluster. And as a result, this allows you to have a very fixed set of inputs. So now, instead of having the 52 options of input, you only have, say, 4,000 clusters. So overall, this is allowing us to insulate T-Light from addresses on the input side, and together with candidate selection, this enables T-Light to be fully insulated from addresses entirely, and it gives it constant storage cost and constant inference latency. So getting to our evaluation, we first compare Twilight against Voyager in an unconstrained evaluation, so we can see the differences in how well they can do temporal prefetching with their respective formulations. And we do so by training them on one portion of a sim point and evaluating them on the remaining unseen portion of a sim point. And as a reminder, compared to Voyager, Twilight has roughly 1,000 less, is 1,000 times faster and is roughly 10 times smaller. So the natural question arises is that what does Twilight have to sacrifice in order to get these massive reductions in latency and storage? And it turns out that it has to sacrifice nothing. It's quite the opposite. The abstraction also enables Twilight to get 4% higher speedup across an irregular subset of Spec 06, 17, and GAP workloads. And furthermore, this extends to across all metrics, seeing 9% higher accuracy and 5% higher coverage. We refer the audience to our paper for more details on how this is possible, that we can sacrifice 6% coverage, yet see higher performance. But the basic gist of it is that the candidate selection enables Twilight to generalize better to unseen data regions, and the option to not prefetch actually plays a very large role in improving prefetch accuracy. Moving on to T-Light's evaluation against practical prefetchers. So again, we are doing this evaluation with, while more faithfully modeling the cost of metadata storage and prediction latency. And we're comparing against the baseline of Triage, which is a practical on-chip temporal prefetcher. And in our first results, we can see that T-Light outperforms Triage by 6% speedup, and likewise sees 3% higher prefetch accuracy and 8% higher prefetch coverage. So one of the limiting factors is that despite all of these reductions, all three neural prefetchers are still too large to be practically trained online, so they're stuck being trained offline. So the only manner of a useful deployment that we can have is that we train it for a particular program and that it can still work across the different program inputs for that program. And to do so, it has two main requirements, in that you can adapt to new addresses and learn new correlations. Unlike Voyager and Twilight, T-Light is capable of doing both of these things because of its two layers of abstraction. The details behind this are slightly beyond the scope of this talk. But the gist behind it is that we can dynamically map new addresses to the clusters accurately, and we can also slot them appropriately into the list of candidates on the fly. So in this evaluation, we evaluate on gap traces across diverse input domains, road networks, citation networks, web, and then we train, validate, and evaluate all on different domains so that we never have any data leakage between any of the domains. And from this, comparing T-Light to Triage, we see a 17% difference in performance. And furthermore, comparing it against the version of T-Light that was trained on the actual evaluation data, there's only a 2% difference, indicating that T-Light is generalizing very well and that it nearly matches fine-tuned performance. And overall, this shows that T-Light is capable of having profitable deployment online. So in conclusion, we have made neural temporal prefetching near practical by significantly reducing storage and prediction latency. And the key idea behind our is our reformulation of the problem, where we abstract away the address space. So any questions?
Hi, my name is Daniel Jimenez. I'm from Texas A&M University. So one question that comes up is, So I want to know, this is awesome, by the way. I think this is great work, and I want to talk to you some more later. How does this compare against the general latest badass prefetcher like Bertie?
So I didn't compare against Bertie in the paper, but I do include comparisons against Pythia. And at equal degree, it does have higher, I can't remember, like 4 or 5%, maybe like between 3 and 5% higher speed up. But I also showed that they profitably hybridize better than, it is better to hybridize Pythia with Twilight than it is to increase Pythia's degree in terms of performance.
And just sort of an observation, so it looks like you're using the neural network to sort of predict the data dependence graph and then prefetch along that. And that could have more applications than just prefetching. It sounds like it'd be cool to talk with you and Calvin later on. But
right.
Good work.
Hi, Alberto Ross, University of Murcia. Nice work. Maybe I missed, which simulator are you using?
For this, I am simulating on ChampSim.
ChampSim. And it's an LLC prefetcher, right? What you are
Correct.
training. Is there any prefetcher at L1 or L2 in the simulations?
For these results, no. But I did have results with an L1 prefetcher, IP stride, and the results are similar.
Okay, thank you.
Thank you. One last question, then we move to the next.
Hello, Georgios Vavliotis, Huawei Research. So great work. The first question is really similar to what Alberto asked, like what is the interaction between having multiple prefetchers in the CASA hierarchy? Would this limit the potential of the prefetcher? And if you have seen any interesting trends. And the second question is...
One question, please. We have to
okay.
Okay, so in terms of having different prefetchers in the hierarchy, it definitely complicates the problem. You have to do a little bit different training, and I think a little bit more work has to be put into that to make it work more effectively. But I would envision that this kind of, my prefetcher would be able to be used more sparingly on accesses that are harder to prefetch and not all the time as well.
Let's thank the speaker.
Thank you.
Right, the next talk is UDP, Utility-Driven Fetch-Directed Instruction Prefetching by Surim Ho. Surim is a fourth-year PhD student from UC Santa Cruz. She's advised by Heiner Litz. Her research interest is computer architecture, specifically on the instruction prefetching techniques.
Thank you very much for the introduction. So welcome. I'm Surim. Today I'll be presenting how we improve the effectiveness of instruction prefetching for data centers. So today's data centers deploys a huge amount of processor cores for their computing activities. And this causes millions of dollars in management and energy cost, and also carbon emissions. So the goal of this work is to reduce these compute efforts in data centers. So to do so, we first investigate the performance of the modern processors. And the modern processors operates the instructions on their pipeline, and the pipeline has two main portions, a front end and a back end. And instructions are fetched and decoded in the front end and executed in the back end and eventually retired. And we want to study how many stalls are spent in each part of the pipeline. And Google has reported how pipeline slots are spent for their Google web search. And almost 32% of stalls are spent doing good work, retiring instruction. And the others are spent in front end and the back end. And almost 25% of stalls are due to front end stalls. And to make matters worse, the instruction footprint size significantly exceeds the size of today's instruction cache, which causes a lot of instruction cache misses. So this large instruction footprint is responsible for a quarter of pipeline stalls. Zooming into today's front end, there is decoupled front end, and in particular, the branch predictor and prefetch engine are decoupled from the instruction fetch. So the branch predictor looks up the branch target buffer and insert the next instruction fetch block into the fetch target queue. And instruction fetch retrieve the next instruction from this FDQ. And if there is a BTB miss or branch miss prediction, then it keeps insert the predicted instruction fetch block into the fetch target queue. So we call all the instruction fetch blocks before any BTB miss or branch miss prediction on path instruction fetch blocks, and all the followings are off-path instruction fetch blocks. So FDIP here is a hardware prefetching technique which emits prefetches for all the entries in this FDQ. And we call on-path prefetches for all the prefetches emitted before any BTB miss or branch miss prediction, and the followings are off-path prefetches. So instruction fetch retrieves the instruction fetch blocks, and when the branch is resolved, then FDQ is flushed. So the one challenge of this FDIP is that it relies on the branch predictor, and the branch predictor relies on the BTB. So if there's a BTB miss, FDIP will never be aware of this miss. And it just keeps issuing too many off-path prefetches on a BTB miss, which is likely for FDIP to pollute the instruction cache with unuseful cache lines. So we can say the front-end stalls have been moved from the instruction fetch to the decoupled front-end these days. So back to the very first motivation, there is large cut footprint in the data center, which generally means there are many branches exceeding the BTB size, which causes many BTB misses, limiting the accuracy of FDIP. So to quantify this problem, we plot the potential speed up of perfect instruction cache over the state-of-the-art FDIP, where every access to instruction cache is a hit, right? So most of the application shows 2 to 40% of potential speed up, and some shows even higher, 4 times, 7 times. So there is a huge room for instruction prefetch. So here are the problems we addressed in this work. So first, why does FDIP fail to eliminate these front-end stalls, and how do we reduce these front-end stalls? To answer the first question, we perform a very detailed analysis on the state-of-the-art FDIP, and based on the observation and insights, we proposed 2 novel mechanisms, UFDQ, which dynamically adapts the FDQ size, the UDP, which prefetches only used for instructions. So let's move on to the analysis. Well, we evaluate 10 widely used data center applications on scale-up simulator, Scikit-Array simulator, and we use in-point methodology. For the detailed evaluation setup, please check out the paper. And first, we studied the run-out distance of these FTQ depths. So let's say we have 2 FTQs with different sizes, one with 4 entries and the other with 7 entries. So FDIP can run at most 4 cycles ahead with a smaller one, and it can run at most 7 cycles ahead with the larger one. This means it emits more timely prefetches because it runs ahead, but at the same time, it also emits more off-path prefetches. So we sweep the FTQ depth to see the impact of the run-ahead distance, and this plot shows the IPC speed up by sweeping the FTQ depth. And most of the application shows that the IPC speed up is going up until they reach the peak, because thanks to the timely prefetches, and after that, it starts going down because there are too many off-path prefetches. more detailed into the timeliness and off-path prefetch and usefulness of prefetches. First, this plot shows the timeliness ratio, where we measure how many prefetches are loaded in time into the instruction cache over all the prefetches, including on-the-fly memory requests in MSHR. So every application reaches their best timeliness at a different FDQ, and timeliness ratio goes up until it reaches the best timeliness. And this figure shows the on-path prefetch ratio, where we measure the number of on-path prefetches over all the prefetches, including the off-path prefetches. So with a larger FDQ, it emits more off-path prefetches. Last, we measure the utility ratio, where we measure the useful prefetches over all the prefetches, including unuseful ones. So we define prefetch is useful if the prefetch is hit by a demand load, and it is unuseful if it is evicted from the instruction cache without any hit. One interesting observation here is some applications benefit from these off-path prefetches, but the others are suffering from these off-path prefetches. So for example, 2 applications on the on-path prefetch ratio at 0.1, meaning 90% of prefetches are on the off-path. Still, utility ratio is 0.1 for one application, meaning most of them are unuseful. But the other shows still 65% of prefetches are very useful. So just limiting off-path prefetches through bandwidth ruling and FDQ depth is not sufficient. So based on these observations, we categorize the data center applications into 3 groups, where off-path prefetches are very useful, or somewhat useful or harmful, or very harmful. So based on this observation, we first propose UFDQ, where we dynamically adapt the FDQ depth based on both utility and timeliness. So we measure the utility and timeliness with a very small amount of hardware cost, and increase or decrease the depth of the FDQ dynamically to reach to the better utility and timeliness ratio. And this achieved 4.9% of IPC speedup by reducing the instruction cache misses. And it turns out, considering timeliness and utility at the same time, only prefetch either inaccurate and untimely prefetches. So now we reach to an optimal FDQ, but we still have too many unuseful prefetches even within the optimal FDQ. So now we learn, with UDP, we learn the usefulness of each prefetch candidate. So first, FDIP still needs to predict if it is the on-path or off-path, because it will never be aware of it is on-path or off-path. So it predicts whether it is on-path or off-path on branch confidence. And if it is on-path, it always prefetch. If it is off-path, then we use the UDP cache. So first, we hold the prefetch candidate until they are consumed with a very small additional FDQ. And when the instruction is retired, the cache line is useful. Now it turns out the cache line is useful, so we insert a useful candidate into the UDP cache, where we use the balloon filter. And then now we query this UDP cache to determine whether this candidate is useful or not useful. So it never prefetch unless the address is in the balloon filter. So it achieves up to 16% IPC speedup and 3.6% on average. So in this work, we address the problem where FDIP fails to eliminate all the instruction cache misses by quantifying the effect of untimely prefetches and inaccurate off-path prefetches. And we propose 2 novel mechanisms to reduce the IKS pollution while still improving the aggressiveness of FDIP. So this is the end of my talk. Please check out our resources. I'll be happy to take any questions.
State your name and your institution before asking.
Hi, Daniel Jimenez, Texas A&M University. Looks like great work. One important thing is, what's the baseline branch predictor?
Baseline of
So you how often you go down the wrong path depends on how good is your branch predictor. So what's the branch predictor?
could you repeat the
What's the baseline branch predictor?
baseline branch predictor? That's a Tage SEL branch predictor.
Okay, how big?
How they
How big?
how
The capacity, the size.
capacity. I really don't remember that. Please check out the details in the paper. But yeah, at this point I don't remember. We can talk offline more.
Yes, we can talk offline.
Yeah.
Hi, this is Cleo from Huawei Research Zurich. I just want to ask you, like, I mean, great work, and I agree that one size doesn't fit all, basically. But I'm confused a little bit if you want to elaborate for the motivation, because I saw that mainly like usefulness and so on, the graphs that you were showing, they actually benchmarks plateau after a certain length of the FTQ. So I mean, for me, it's not direct, you know, the need for like different FTQ size to grab the performance, but I'm not sure if you want to.
So can you?
So I mean, in the plots that you were showing on the motivation about the FTQ size variance and usefulness and utility ratio, I think that what I was seeing is that they plateau after a moment, like across an FTQ certain size. So I'm not sure that I get the point that it needs a different FTQ size.
Okay, so by sweeping the FTQ size, we're seeing the different timeliness and usefulness behavior. So of course, the timeliness ratio goes up with the deeper FTQ, and also the utility ratio goes down with a deeper FTQ. But what we are seeing here is that application shows different behavior. Some are some benefits from the off-path prefetches, and then the others suffers from the off-path prefetches.
Okay, so thanks.
Yeah.
Okay, yeah. So we have room for one more question.
Georgios Vavliotis, Huawei Research, great work. So my question is again about the workloads. In the second slide, I guess, where you differentiating the FTQ size, I have seen only 2 applications like really showing a change when you increase the FTQ size, while the others kind of are modest in changes. So I didn't have the chance to look at the performance results in the end. So I'm wondering whether the benefits are mainly for these 2 applications. I think it was very later and XGBoost.
Yeah.
And the other ones, kind of, it was.
Yeah. So
I just want your thoughts on this briefly. Thanks.
So yeah, that's a good question. So XGBoost validators are very extreme cases. So we are seeing these applications shows that the off-path prefetches are very useful or like very harmful. But we're also still seeing for other data center applications, they are somewhat useful or harmful. So it was effective to filter out some unuseful prefetches from them. So we are seeing like meaningful IPC speed up by filtering out some unuseful prefetches.
All right, thank you. Let's thank the speaker. Right, the third talk of this session is about Triangel, a high-performance, accurate, timely, on-chip temporal prefetcher. And the speaker is Lev Mukhanov. He's a lecturer at Queen Mary University in London. His research interests are systems, compilers, DRAM's fault resiliency, and energy efficiency.
So, good afternoon. Thank you for attending the last session. Okay. So, yes, today I just would like to present another work on a temporal prefetcher. So this work actually, it was driven, industry-driven, and the work itself was mostly done by Sam Ainsworth, and it was driven by him. So basically we have a kind of a big project. We're working software, hardware co-design. And just Sam in this project particularly focus on the hardware side. So while I'm on the system software side. So yes, so just background about so yeah, we are working on cheap temporal prefetchers. So the basic idea is very simple. You want to apply it to a regular access pattern and want to prefetch a regular access pattern, and basically like A, B, C. And you just store this information as a metadata, in format of markup table. So basically it stores the pairs of A and B. It's just a short introduction. And regarding as I mentioned, so it was industry driven, and we just want to understand what happens, who implemented, and so on. So ARM introduced this CRC, correlating missing chaining. And unfortunately, there's only a few details available. And they also introduced was triage, which was mentioned today, so at Micro 2019, and there was extension of triage ISR. So triage was our baseline. So now, just what is triage? So yeah, all the prefetcher happens at L2 level, and it actually implements the training table, which contains PC and previously accessed data address. And it also implements the so-called metadata table, where you stores all the pairs, like A, B, or B, C, and so on. So in this example, so when you just access for PC'24 dead B0, so, and the previous address was dead B, so you basically add to the meta table add B, add B0, the pair, this pair. So yeah, one more important thing is that the metadata stored, allocated dynamically and L3, and it is dynamically allocated partition. So the training happens on miss and prefetch hit. Yeah, so what's the problem with triage? So there's one big problem, that there are many details which are actually not clear, and you need to make a kind of reverse engineer or just make some assumptions, and that's what we do. So we implement both triage and Triangel version. So why we introduce a new prefetcher, which is called Triangel? So the problem of the triage itself, it is that it's not accurate. And the reason for this is that actually does not detect the repeating sequences. So in other words, it does not have confidence mechanism which evaluate how often the sequences repeat. So so it means that it can be inaccurate, and the major issue is that, again, it's industry driven, and when you try to implement this on a real chip, it means that you increase L3 traffic and DRAM traffic. And another thing, when it's accurate enough, so it means that it's not aggressive enough. And basically what we did, we addressed these particular issues. So we implemented a specific, we extended triage and implemented so-called stochastic-based history sampling. So that mechanism enables us to detect, to track different sequences and increase their confidence, and measure the confidence, how accurate will be prefetching. It will start prefetching for this particular PC. We also use the reuse flags, and we also introduce a new kind of techniques which I present a bit later. So it's a look ahead, and so basically it's about improving the accuracy, and we just implement the sampling mechanism for this. So now here you see the architecture of triage. It has a training table as or Triangel, I'm sorry. It has a training table as a triage. It has confidence lag. It implements two-level sampling. I'll explain why a bit later. It also implements a set-dueler mechanism. So why do we need a set-dueler? The problem is that we need dynamically control the size of the metadata. And So basically, the problem is that if you understand that your prefetcher is inefficient, if you allocate the metadata, so you just will degrade the performance. So this is why we implement Duong, which decides the size of a partition. So yeah, we also implement reuse buffer, and reuse buffer enables us to actually reduce the pressure on L3 when it becomes too aggressive. So yeah, let's switch quickly to the history sample, so how it works. So history sampler just implements a very small table and samples the pair of addresses, let's suggest A, B, which you want to kind of prefetch. And it implements a time steps, and based on these samples of the addresses, it's trying to, again, set the flags of how confidence which this pattern will be efficient to prefetch, how often it repeats, and the reuse distance. So we also take into account reuse distance. So in other words, we're trying to only enable prefetch for those PC which kind of within the capacity of a temporal prefetcher. So why do we need the second chance sampler? So the problem is that when you have sequences like A, B, C, D, it's fine. But if you have sequence, let's say as here, for example, you have a sequence X, Y, and X, Z, right? So in a triage, you can store only one sequence, right? So X, Y, or X, Z. And basically what the second sampler is trying to do, it's also trying to consider these sequences. So when, for example, you have several successors, and judge, based on the sequences which it sees, how, in general, will it be efficient to prefetch or not. So the set dueler mechanism, just as I mentioned before, it's just helps us to find the optimal metadata size. So metadata, it's the Markov chain table called. So yeah, in the previous work, they also was mechanism to find the size of the metadata, and they have been triage user. They have been using Bloom filter, but we actually show within the paper that Bloom filter is not really efficient. So we implemented set dueler. I'm not going to cover the details. I don't have time for this, but I want to say that set dueler is kind of very smart mechanism because it enables you to consider all the possible combinations at the same time. So it enables you to actually predict and estimate the performance of a L3 with enabled meta-prefetch and with disabled meta-prefetch. In other words, it's just measure the misses. If the misses, just the rate of the misses without meta-prefetch was higher, it just would prefer to disable the temporal prefetcher. So another thing which we introduced also in this work is just look-ahead mechanism. So we prefetch, we have a mechanism to prefetch not like one element, so in the sequence one by one. So for example, you prefetch usually A, B, C, D. So we actually can prefetch with a step 2. And after A, we can prefetch C. Why do we need it? The problem is in linked list, you usually see that when you access A and you prefetch B, it's already too late. So you need, at the moment when you access A, you need to prefetch C. So we also implemented the high degree prefetching mechanism, which increases how many prefetchers you implement when you see the fitting when you match to the particular data in Markov table. So it's as a triage we implemented the two, but we improved the again accuracy mechanism. So here you see just the configuration which we have been using in our experiment. So we have been using Gem5. All the implementation is available in Gem5. So it's everything we implemented: triage, Bloom filter, hockey, replacement strategy, and so on. So you can find everything there. So we have been running. Was making experiments with 7 workloads, which has implement the irregular memory access from spec 2006. So here you see the results. So the first, what you see, so we implemented, here you see 5 configuration triage, default triage. Again, it's important to say this is our interpretation of triage. So, and you see also triage degree 4. It means that how many prefetchers you do at the same time. You also see the triage degree 4 and look ahead 2, and also implementation Triangel and Triangel with Bloom filter. So what is important here is that we see that triage gives 9% speed up, while just Triangel gives 26. But what is much more important, again, if we are talking about the real chips, so it's a DRAM traffic. So the DRAM traffic, while just triage just has just 30%, and if it's aggressive, it becomes more than 40%, while Triangel just give about 9% traffic overhead. Finally, just I want to say that Triangel is more accurate than the triage, but sometimes has a lower coverage. But it's reasonable to low coverage. Why it has low coverage? Because it's actually dynamically decides when to prefetch or not, when it's efficient prefetch or not. So it's more accurate in terms of efficiency, overall efficiency. So, and I just want to say also one more example about that, how Triangel detects when it becomes not efficient to use the, to allocate the metadata. So, for example, on OnNet, based on set dueler mechanism, it's just disabled the temporal prefetcher because it was not efficient. It decided that it will not be efficient to prefetch. So basically, that's it.
Right.
Thank you.
Let's thank the speaker. Question? State your name and institution.
Georgios Vavliotis, Huawei Research, great work. 2 questions. The first one is whether you considered any evaluation with first-level cache prefetchers and whether having more and more prefetchers in your baseline would impact the training of the prefetcher and would impact the performance results. And the second one is whether your prefetcher is trained with virtual or physical addresses and
okay. So second question, physical, which is not realistic. Second, the first question, L2, no, we didn't put the meta, so we we have made experiments, but the problem if you allocate the metadata in L2, it's just the capacity is not enough. So basically the problem of that, how many addresses you can cover in DRAM is very limited compared to if you allocate an L3. It's just capacity problem. There's another issue. So when you allocate the data in L3, there's another issue, again, if you go to real chip.
Maybe one question I may have missed in the talk. What's the cost of implementing Triangel, in hardware cost?
Well, it's quite small, but it's definitely much lower than triage, because triage implements Bloom filters and so on, which is very heavy. And we also optimized they also implemented lookup table. We all optimized this. So basically, it's definitely lower. I don't recall the exact numbers, but it's much lower than triage.
Right, let's thank the speaker.
Thanks.
Right, our next talk is alternate path fetch, and the speaker is Aniket. He's a 7-year PhD student from UT Austin. He's planning on graduating very soon. His research interests include anything CPU microarchitecture, particularly the front end. The floor is yours.
Thank you for the introduction. I'm actually going to get right to it. So the main, goal of our work here is to save the branch misprediction penalty. Now, I'm sure this is no surprise coming from our research group, but branch prediction is still a problem today. And even with Tage and Perceptron, which have an extremely high accuracy, there's still a gap between perfect conditional branch prediction and what we have today. If we measure this for spec integer and gap benchmarks, I did a small study here, we see that relative to a 64 kilobyte Tage SCL baseline, perfect conditional branch prediction can give us up to 55% performance improvement, even 2x or 3x performance in some select workloads. And of course, this is without improving memory, and as I'm sure most architects know, improving memory along with branch prediction is where the value of improving branch prediction really lies. The problem in recent years is that investing into predictor capacity hasn't brought us as much performance. This is because there are two classes of branches that we're struggling to deal with. One class is branches that we can still predict using current algorithms, but there are so many patterns that building hardware tables for it would be infeasible. Another class is that of data-dependent branches, branches that directly depend on input data, which is relatively random, in which case history-based predictors just don't help with these branches. Academia has tried to bridge the gap by proposing alternatives to branch prediction. However, most of these solutions generally have a low misprediction coverage because they target specific control flow behaviors. For example, something like dynamic predication requires a short hammock and a predictable convergence point, or precomputation requires backward slices that are control independent, data independent to get most of the performance. And so what we're really missing here in this space is a solution that works for any conditional branch misprediction and also has a relatively high misprediction coverage. Before I get into our solution, let me just make sure we're on the same page about the timeline of a branch misprediction. A branch is predicted in the first few stages of the out-of-order front end, but the misprediction is only detected when the branch reaches the back end and finishes execution. This duration is the branch resolution delay and is a minimum of 14 to 18 cycles, depending on your pipeline design, but often much longer because branches need to wait on their input dependencies to resolve to finish execution. After the branch resolves, instructions younger than the mispredicted branch are flushed, and we can start fetching instructions on the correct path. However, the correct path instructions don't begin doing useful work immediately. They need to flow through the pipeline and reach the back end, and this duration is called the pipeline refill delay. The pipeline refill delay is essentially the front-end latency and amounts up to a third of the total misprediction penalty, even a half of the total misprediction penalty in some benchmarks where branches resolve very quickly. And so our work is targeted at just this pipeline refill delay. We hope to get as much performance as we can just by saving pipeline refill delay for as many branches as possible. So in a nutshell, alternate path fetch performs fetch, decode, and renaming for instructions on the alternate path of an often hard to predict or H2P branch, as opposed to the predicted path, which is what the branch predictor tells you to do. And I'm going to use a little example here to demonstrate exactly how it works. Let's say we go along in the control flow and hit hard to predict branch A. The PC and the branch history are updated with the prediction, and that is what I refer to as the predicted path of A. We have a copy of the PC and the history register, the alternate path PC and history, if you will, which is in fact updated with the inverted branch prediction. This essentially forms the alternate path of A. In addition, we have a dedicated front end with duplicate fetch stages and duplicate rename stages, decode stages, which process instructions on the alternate path in parallel with the predicted path. So once the PC and the history for both paths have been set up, we can actually begin fetching instructions and processing instructions down both paths. Of course, we may actually encounter future hard-to-predict branches on either path. We encounter hard-to-predict branch B on the predicted path of A, and X on the alternate path of A. Now, we don't do anything for these other hard to predict branches yet, because that would cause an exponential explosion of the number of paths. Instead, we simply save the PC and the history at these hard to predict branches. I just want to mention that this is actually a very common scenario, because in most benchmarks, hard to predict branches tend to be clustered together. We process instructions on the alternate path until we reach the end of the alternate path front end, in which case the instructions are gathered together and saved into a buffer on the side. This frees up the alternate path front end to process instructions for another alternate path. In this case, we start processing the alternate path of B. Note that we're able to begin the alternate path processing for a hard to predict branch B well after the branch was fetched. That's because to begin alternate path fetch under our model, you only need the PC and the branch history at B, which is actually already saved in modern out-of-order cores in an in-flight branch queue or a branch tracking table. Now, once branch A resolves, one of two things can happen. If branch A was correctly predicted, then the alternate path of A is discarded, and we continue doing what we were doing, which is fetching the alternate path of A, alternate path of B, and the predicted path of B. However, if branch A is mispredicted, we take the contents of the alternate path of A, which we had saved, and restore it to the main pipeline. So we override the PC and history register, override the pipeline registers, and now the main pipeline it's as if we cycle through all those instructions, except it doesn't take the full pipeline refill delay to do this. It's much faster because we have these instructions saved. Moreover, since we've restored the PC and the history at the end of the alternate path of A, we can actually begin fetching from where we left off. This is a pretty important point, because there's been prior work where, such as misprediction recovery caches, where you just replay a stream of instructions after a mispredicted branch that you've saved. However, the problem with just replaying a stream of instructions is that you either replay the predictions for that stream, which is not that great because saved predictions are very inaccurate, or you have to restart fetch again from hard to predict branch A. In our case, we actually have we don't have a separate port to the branch predictor, but we bank the branch predictor, which allows us to predict branches on the alternate path. One more thing is that we can also begin doing alternate path fetch for branch X, which was encountered when we were doing alternate path for A, after restoring the contents of the pipeline, because we also saved the PC and the history at branch X. Okay, I'm going to quickly go over some of the key design decisions that we faced when dealing with the alternate path fetch. So the first question is, for how long do we process instructions on the alternate path? We stop at RAD accesses. This decision seems interesting because the longer you process alternate path instructions, the more benefit you're likely to get. But the problem with going beyond this, the problem with doing RAD accesses and modifying the state of the free list, for instance, is that the state associated with each alternate path now includes the state of the RAD and the state of the free list as well. If you go further and allocate these instructions into the ROB and the reservation stations, then they induce additional allocation pressure, and you have to remember those positions as well. We wanted to keep each alternate path lightweight so that, as shown in the previous example, we can start alternate path fetch at any H2P branch, and that's why we decided to stop at RAD accesses. And there's we've evaluated this in the paper and found that this was best for performance. I won't go over this in detail, but the way we picked hard to predict branches was a combination of Tage confidence, which uses the saturation counters within Tage, and a custom hard to predict table that measures the average misprediction rate of a set of static branches. This allows us to get both prioritize important branches and get good coverage. Finally, I mentioned predicting branches on the alternate path. While we do duplicate some of the front-end stages, the main overhead in the front end comes from the iCache, BTB, and branch predictor. We don't want to build an additional port for these, so we developed a banking scheme for all these structures. Banking the iCache and BTB is, well, if it's not already done, it's relatively simple, but banking the branch predictor hasn't been explored before. And that's what we did. We didn't try anything complicated. All our banking scheme does is takes the baseline 64 KB stage and break it up into 4 smaller 16 KB stages. A branch is statically mapped to one of the 4 stages based on its PC. We take a hash of the PC, and if the hash of the PC reads 0, it's mapped to the first stage. If the hash of the PC reads 3, it's mapped to the last stage. What this allows us to do is send both the alternate path PC and history and the predicted path PC and history to all 4 stages. If there's a hit in, if both those PCs go to different stages, then we can actually get 2 predictions every cycle. Moreover, of course, there can be bank conflicts, and on bank conflicts, we prioritize the predicted path. Just a quick overview of the performance. The upper graph shows the MPKI corresponding to the benchmarks we evaluated, and the lower graph shows the corresponding percentage speedup that APF provides. Geomean, it's 5%. And at first glance, you can see that the MPKI of the benchmark maps very closely to the amount of performance improvement we get, which makes sense because higher the MPKI, more the opportunities to fetch down the alternate path. In conclusion, APF provides a simple solution to reduce the misprediction penalty for any conditional branch. And this adds a certain flexibility because it allows us to combine the solution with others. Let's say there's another solution that improves a specific set of branches. APF can simply target the branches that are not improved by this other solution and still provide additive benefits. Finally, our TAID scheme provides a simple mechanism which we're currently using to predict branches on the alternate path, but we see this could be also used for something like prefetching. Thank you very much.
Thank you, speaker. Question, name and institution.
Hi, I'm Daniel Jimenez from Texas A&M University. I'm going to ask you one of these jerk questions. So, there's been a lot of work, a lot of previous work, going various depths down more than one path, eager execution, and then there was less ambitious studies where we just focusing on fetch. And I haven't read your paper or reviewed it, but I want to know, is in your related work section and or in the reviewer comments that you got, how do you distinguish this from that previous work? And what's the sort of kernel that makes this right?
I think I have a figure in my presentation that sort of summarizes this pretty well. It's also in the paper. If they could put that up. Okay. So the idea is that if you go beyond just detecting dependencies and start modifying the state of the RAT, what you're doing is you're sacrificing coverage because you cannot feasibly save the state, which is now the registry alias stable state, the free list state associated with each alternate path. So what you're forced to do in order to save up on area is just go down certain alternate paths. Whereas what we can do, because we stop where we do, is we just use the PC and the branch history. This is already saved for a large number of branches in the program, so we can target any one of those branches. And our performance benefit really comes from the improved coverage that this buys us. And the paper does have an evaluation of the various depths we can go through and how much performance that would give us, and APF does come out on top in those cases. As far as eager execution is concerned, if we go down and actually end up executing instructions, that can cause back-end pressure and causes other complications like managing multiple registry alias stable states. We wanted to keep the solution simple, and that's why we stopped where we did.
Thanks.
Yeah.
Who
Who's next?
Sorry, Klaulos Kalajidis from Huawei Research Zurich. I see that you mentioned about banking, which makes perfect sense generally for fetching more than one. I want to ask if you are limited by the iCache port contention or so, since you're
yes.
parallel.
Yes, so we model port contention on the iCache, BTP, and branch predictor. You would expect that the port contention, that the bank conflicts as a result of all of the contention would be around 25% because we actually bank 4 ways. But we actually saw a much lower bank conflict ratio, 10%, because we use the lower bits of the PC to bank both the iCache and the branch predictor. The idea being instruction streams usually flow sequentially, and if we use the lower bits to bank, if we have a bank conflict, following that bank conflict, the addresses of the alternate path and predicted path are offset, and now any future accesses will have much fewer conflicts.
Thanks.
Yeah.
Last question.
Very nice work. Alberto Ross, University of Murcia. You use, so the Tage confidence predictor by Deshmukh uses 3 levels, medium, low, and high confidence. But it seems that you only use low confidence.
I only use low confidence, right.
Okay.
We didn't actually play around too much with Tage confidence.
So the question is, if you have any analysis with medium confidence too, and how much on top of that adds the dedicated hard-to-predict predictor?
So the paper does have a little bit of analysis regarding how much Tage confidence helps. We found that Tage confidence accuracy was around 12, 13% or so. That's why we added the H2P table to back it up. And the whole purpose of that was just to provide a large coverage, just provide target branches that Tage confidence doesn't say it's low confidence, but these mispredict on average quite a few times. So we want to do something for them too. Yeah. But yes, this could definitely benefit from a more advanced confidence mechanism. Yeah.
Thank you.
Yeah.
All right, let's thank the speaker. All right, we have the last paper of this session.
Thank you guys for sticking around till now. So thank you for the introduction. I'm Savan, and today I'm going to present our work, Alternate Path, Micro-op-Cache Prefetching. So in this talk, we will focus on micro-op-cache. So micro-op-cache is a small structure that holds recently decoded micro-operations. It was first introduced for energy saving in x86 architectures because they require complex decoders. But we found out that micro-op-cache can also provide significant IPC improvement. In our study, we found out that ideal micro-op-cache can provide an IPC improvement of up to 10.82%. Thus, we propose UCP, Alternate Path Micro-op-Cache Prefetching, which identifies a hard-to-predict branch and then starts prefetching the micro-operations from the alternate path to the micro-op-cache. So we will first look into the processor front end. So here you can see that a modern-day processor front end where the target prediction comes from the BTB, indirect predictor, or RAS. And then if the branch is taken or not is determined by the branch predictor. Then depending on if the branch is taken or not, the target is used. Once the next address is predicted, it is inserted into the fetch target queue, or FTQ. FTQ is responsible for fetching the instructions. Now, in current modern-day processors, the processor has 2 paths to fetch the instructions. One is the legacy one, where the instructions are fetched from the L1I. Now, once the instructions are fetched from the L1I, they have to go through the decode, and thus they have to pay for the decode latency, the decode energy, and generally the bandwidth is a bit lower. Now, the other path the processor can use is the micro-op-cache path. Micro-op-cache holds the decoded instructions, so you can skip the decode latency. You don't have to pay for the decode energy, and generally it provides a better, it provides a higher bandwidth. So let's look at the performance of micro-op-caches, especially for server workloads. So server workloads are very popular, especially for their large footprint, and as micro-op-cache they are a bit small, and thus the server workload overwhelms the current micro-op-caches. We found out that implementing a 4K micro-op cache over no micro-op cache baseline only provide 0.87% IPC improvement. We also did a test where we increased the size of micro-op cache, and we found out that it does not help a lot. So as you can see here, on the x-axis, we have the IPC improvement with respect to a 4K micro-op cache. And on the y-axis, we have the increasing size, starting from 8K micro-ops to 64K micro-op. And the IPC improvement only reaches 1.18%, while we saw that micro-op cache can provide an IPC improvement of around 10.82%. So there is still a huge gap, even if you increase the size. So the key insight here is that for server workload, even if you increase the size of the micro-op caches by 16 times, the IPC improvement you get is still not close to the potential. Now, FTQ is unable to hide the L1I mislatency when there is a branch misprediction, as it was explained by previous presenters as well. So this happens because on a branch misprediction, the FTQ is cleared. So let's see that we have example here at branch B, and you have a predicted path as well as you have an alternate path. So FTQ is able to hide the mislatency in this case if the predicted path is correct. If the predicted path is incorrect and thus the alternate path is correct, the FTQ will be cleared and the FTQ has to start over. And thus, it is unable to hide the L1I mislatency in this scenario. Now imagine a scenario where all the instructions that you fetch after branch mispredictions are already in the micro-op cache. So we see this diagram before. Now let's see this. So the 8 branches here, it shows that all the instructions till we reach 8 branches are already in the micro-op cache. And this promises our IPC improvement of almost double compared to increasing the size by 16 times. If you relax the limit a bit to 16 branches, the potential is around 2.9%. So here we have 2 main key insights. The first one is that FTQ is unable to hide the mislatency if there is a branch misprediction. Second, focusing on few but very critical instructions can provide a greater part of the potential. So for having that in mind, we propose micro-op cache prefetching. So UCP or micro-op cache prefetching works on 3 main elements. The first one is to identify a hard-to-predict branch. The second is to start generating the addresses on the alternate path. And the third is to prefetch those addresses on the alternate path to micro-op cache. So the main key idea of UCP is to have the alternate path ready in the micro-op cache, especially for hard-to-predict branches. So the step 1 is to identify a hard-to-predict branch. Hard-to-predict branch is a branch that has a very high possibility of getting mispredicted. So we built up upon Tage confidence. So Tage provides predictions either from hit bank, alt bank, or prediction from the bimodal. Here you can see in the graph, you can see the different confidence value and the difference miss rate. In Tage confidence, all the predictions that come from the non-saturated counter are considered as hard to predict branches. But we notice, and we built up upon this, and we notice that if you look at the alt bank, even if the counter is saturated, you still get a very high miss rate. Also, the Tage conf only uses Tage components like hit bank, alt bank, and bimodal. But in Tage SCL, you also have a statistical corrector. If you look at the statistical corrector, you will see that it also exhibits really high miss rate. Thus, UCP considers all the predictions that come from alt bank and statistical corrector as hard to predict. Using these 2 insights, UCP managed to improve both the coverage and the accuracy of a hard to predict branch. Now that we know how to identify a hard to predict branch, we need to start generating the addresses. To generate the addresses, we will need a branch prediction unit. Now there are 2 ways. First, we can either bank the structures or we can add a new predictor. But as most of you know, that for server workload, BTP size is very critical. And thus we decided to increase the number of banks from 16 to 32 and share the BTB with the demand path. For other predictor, we decided to add a small 8 KB Tage SCL, a 4 KB IT Tage, and a small 16 entry RAS to generate the addresses on the alternate path. as the previous presenter said, we can even bank these structures and you can get rid of the overhead. Now, once you start prefetching, once you start generating the addresses, we need to know when to stop, because it might be possible that the alternate path is no longer the correct path. Now, to identify this, we assign weights to each branches that appear in the alternate path. The weight defines if the prediction is confident or not. So high confident branches gets lower weight, and low confident branches get higher weight. Here in the graph, you can see that for the hit bank, that the counter that are saturated get lower weight, while the counter that are not saturated get the higher weight. Now, UCP accumulates these weights, and once it reaches a certain threshold, we stop the path. Now, BTB miss on alternate path is a clear indication that the alternate path might not be the correct one. So UCP stops on a BTB miss. Also, if you have a new hard-to-predict branch, to be under hardware constraint, we do not allow two parallel alternate paths. And thus, when a new hard-to-predict branch is detected, the previous alternate path is stopped. Now we know how to identify hard-to-predict branch. Now we know how UCP generates the addresses. Now we look at the prefetching. So for that, all the generated addresses are added to a small FTQ, alternate FTQ, and from there we do a check to micro-op cache. If the entry is already in the micro-op cache, then we do not do the prefetch. If the entry is not in the micro-op cache, we add it to the MSHR, and from MSHR we add it to the L1I prefetch queue. From L1I prefetch queue, the entries are either fetched from L1I cache or from L2 or LLC. Once the entries are fetched, we add them to the alternate decoder, and from there we fill the micro-op cache. Now, to test our idea, we use ChampSim. We use Intel Adder Lake-like microarchitecture. We use a subset of CVP traces that were fixed with the recent proposal, and we use around so our subset includes the traces that show a potential of around 5% improvement with ideal micro-op cache. We execute 100 million instructions, 50 million for warm-up, and 50 million to collect the stats. So the main results we have is the IPC here. So in the x-axis, we have the storage in KB, and on y-axis, we have the IPC improvement. First, we look at the previously proposed L1I prefetchers, and you see that they do provide performance, but on cost of very high hardware overhead. Now, the first proposal is UCP, where we only prefetch till L1I. And in that case, it provides an IPC improvement of 1.7 and outperforms all previously proposed L1I prefetcher. Now, once you have the prefetch, you can decode them. To decode them, you can either use the shared decoder, that means the alternate path and the main path will share the decoders. In that case, UCP provides around 1.8% improvement. If you have your dedicated decoder, the UPC can provide an IPC improvement of 2%. Now, as I said before, that we bank the BTB. Thus, it might be possible that we have BTB conflicts. So imagine a scenario that there is no conflicts. And in that case, UCP has the potential to provide an IPC improvement of around 2.2%. Now, we also tested by increasing the size of stage SCL by 2 times, and still we found out that UCP still performs better. Thus, to conclude, we want to say that, okay, micro-op cache was introduced for energy efficiency, but micro-op cache can be useful to provide IPC improvements. And we propose micro-op cache prefetching, which identifies a hard-to-predict branch and prefetches only the critical instruction to micro-op cache. We have our artifact open source, and we would love everyone if someone wants to do a test or extend it. Thank you.
Thank you, speaker. Questions?
Daniel Jimenez, Texas A&M University. There are lots and lots of questions I could ask, and I will ask you after the talk, but I think I'll leave you with one comment, because I know Alberto is very good at this. I think there's a lot of potential in looking at fine-grained confidence estimators for branch predictors. And you leverage this in your paper, but I think there's a lot more you can push on that to identify those hard-to-predict branches. And I'm going to stop myself. But great work.
Thanks.
(2024), and the big thank you to the general chairs and all of the conference organizers for this fantastic conference, and that includes the Hilton staff, so a big thank you to the staff as well. Hope to see you at ISCA 2025 in Tokyo.